Now I want to move on to cycles. Well, I mean, we've seen cycles a bit, but we're going to look at cycles in much more detail at present. Before we go on, let me sort of give you again the definition of cycle. We'll take our time, okay? So if we have a graph, G of X and U, so X, I'll remind you, is the vertex set, and U is the set of arcs. Then a cycle is a sequence of arcs such that each arc has one endpoint in common with a preceding arc. So if I call UK the kth arc in the cycle, then UK and UK minus 1 share an endpoint, and the other endpoint is shared with the k plus 1th entry in the cycle. Okay, so we have a chain of arcs that is defined that way. Another thing is that this sequence does not use the same arc twice. And we have a cycle because we cycle back to where we started. Okay, so the initial vertex and the terminal vertex of a chain are actually the same. And if additionally we only encounter each vertex a single time, except of course the endpoint and the start and the beginning, then what we have is an elementary cycle. Okay, so I'll give you an example right away. So consider this graph here. So I have 4 vertices, A, B, C, and D, sorry. And I have a certain number of arcs, which I've labeled from 1 to 6. Okay. Now, here I'm going to look just at elementary cycles, and I'm going to claim that these are the only elementary cycles that we can find. Actually, there's a bunch of others, but we are going to restrict our way of thinking to, like, we're going to say that 2 cycles which end up doing the same thing essentially are the same. So for simplicity, I'm only going to look here at cycles that start at A. Okay? And you can see the cycles that are denoted here. So the first one, and I'll call it mu superscript 1. It's not an exponent, okay? It's just a 1. And it's the cycle that goes through through arc 1, arc 6, and arc 2. And this is an important remark here. That first cycle points out something that is really important, which is that we can take arcs in the wrong direction, okay? And you can see that cycles 1 and 2 essentially follow roughly the same path, except that there is one that follows that arc in this direction, okay? It goes A, B, C, A, following arc 2, the opposite way to the orientation of the arc. And cycle 2 here does the same thing, but this time it follows this arc in the positive orientation, okay? It follows it in the direction of the arrow. And this is going to be important later, okay? Now, there's another elementary cycle which goes A, C, A, and it's elementary, okay, because I am not using the same arc twice. Indeed, I'm going just A, C, A, and I'm not going to list the other one. Obviously, I could think of going A, C, A, but taking 3 the other way and 2 the other way. this is not really important because I'm going to meet the same arcs and the same vertices on my trajectory, on my travel, and therefore you'll see later we'll actually think of the one that does 3, 2 would be minus the one that does 2, 3. Okay, we'll see this in a little while. And then there's this one that does A, B, D, C, A, A, B, D, C, A. And this one and that one are the same in terms of the order of the vertices that it meets, but they are different in terms of the arcs that they follow, because that one uses 2, whereas that one uses 3. Okay? And the last elementary arc that we have is this one that goes A, C, D, B. Okay? So these are the elementary cycles here. There are many more cycles, of course. The elementary ones meaning that I'm not using the same arc twice. And as I pointed out, you could very well think of, for instance, this ACA. You could also think CAC. But that's essentially the same thing. Okay? We meet the same two vertices following the same arcs. So they're essentially the same. And typically, we'll try to keep things as simple as possible. Now, I just mentioned just before the fact that when I was following this first cycle here, A, B, C, A, I did A, B, C, and I followed that arc here, that arc number 2 in the wrong direction. And the way we're going to denote this is that we are going to write mu plus the set of all the arcs that are followed in the direction, like in the proper, when you follow the arrow, you put a plus. And when you go counter to the arrow, you put a minus, okay? And if I number the arcs in the graph as 1 to m, as we have done here, okay, 1 to 6, the 6 arcs, I've labeled them 1 to m, then I can think of a cycle as a vector that says how each arc is traversed, whether it's going in the positive direction or the negative direction, or if it's not traversed. So that, let me go back to this previous example. If I think of mu1, I can write mu1 also as follows. So I'm indicating whether I'm following an arc in the positive direction with a 1 or the negative direction with a minus 1. And if I'm not following an arc, I'm giving it the value 0. So the first arc is 1, and I'm following it for mu1, okay? I'm following it in the positive direction. The second arc is 2, okay? So here I'm doing things in the order in which things appear in terms of the labeling of the arcs. The second arc is 2, although in the path, it is not, in the cycle, sorry, it's not the second thing I do, okay? And I can then say that I'm following 2, in this case, in the negative direction. I am not following 3, neither 4, 5, and arc 6 I'm following in the proper direction, well, in the positive direction. This is weird, so I am getting very little light above this. This is interesting. Okay, maybe I'll try another color. We'll see if this works better. So this is 1 minus 1, 0, 0, 0, 1. Okay, the same way mu2 would be the vector. So I'm following 1 and 6 in the same direction. The only difference is that I'm now following 3. So I'm following 1, 6, and 3. 3, so I'm not following 2 anymore. 3 is followed in the positive direction. 4 is not used, neither is 5. Okay. So I can think of these cycles as vectors. Okay, this is a vector with a certain number of entries. The number of entries, of course, is the number of arcs. And I'm explaining this way how I am following these vectors, these arcs. Okay, so this is what this is saying here. Okay, 0 if I am not following the arc in my cycle, 1 if in the positive, or plus 1 in the positive direction, minus 1 in the negative direction. So something we won't be using much, but that will come up in some definitions, therefore I'm giving you the definition, but don't worry about this too much, okay? We'll call, so take a subset of the vertices. Remember, X is a vertex, the vertex set. Take a subset of the vertices and denote omega plus of that set, the set of arcs that only have their initial endpoint in A. Okay, so this is, so remember I said we'd do potatoes. So I have a bunch of vertices in A, that's the set of vertices, and I'm going to denote omega plus the arcs like this one and this one that come from outside the set A and have the terminal endpoint, their initial endpoint. I'm going the other way. Yes, sorry. This, I'm finding that the thing is a little small. The TV that is a bit farther is not really good, and the plus and the minus on top of the omega are barely visible from here. I hope they show properly on the videos. I'll check that because here I'm having really big trouble seeing the plus and the minus. Okay, so these would be, sorry, I take that back. These would be in omega minus. And the set of arcs that initiate in A are denoted with omega plus. Okay. And we denote omega of A, the union of these arcs. Okay. The ones that have their initial endpoint in A and the ones with their terminal endpoints in A. So what we call a co-cycle, it's a non-empty set of arcs that have the form of this omega of A. Okay? And we'll partition the co-cycle into the two sets, omega plus and omega minus. The same way as we define an elementary cycle, we can define an elementary co-cycle, and this is going to be the set of arcs joining two connected subgraphs, A1 and A2. Okay, so remember that a subgraph is a graph that I obtain by taking a subset of vertices, and so if I have a graph, and I call this A1, say, and this A2, then the subgraphs A1 and A2, they correspond to, so I would forget this guy here. And actually, an elementary cocycle would be a set of arcs joining two connected subgraphs. Both of those subgraphs are connected. Okay, and so that would be an elementary cocycle. Okay, the intersection, so the two subsets are not empty. This is the first condition. The intersection between the subsets is the empty set. So that means there are no vertices that belong to both subgraphs. And the union gives a connected component of the graph. And this is a connected component of the graph because remember that for connectedness, we're not looking at the direction. The same way as in a cycle, we're not looking at the direction. We can follow arrows the wrong way. For connectedness, we can follow arrows the wrong way. We just want to see that there exists a chain that will take me from one vertex to another. Okay? So that's what a cocycle is. Now I'll give you, you'll see many of those. This is just for interest. We might see a few other such results, but just for your interest in general, I'm going to give you what is called a coloring lemma. So if I have a graph with arcs from 1 to m, and I start and I color, this is something we do a lot, okay? We color an arc, so we just say, let me paint that arc black. And then I take the remaining arcs and I paint them red, black, or green. Then one of the two following things can happen. I can either find an elementary cycle that contains the first arc that I colored black, okay, arc 1, and the remaining arcs in that cycle are only going to be red and black, with the property that the arcs that are painted black all have the same direction. Okay. Or, so this is an exclusive or. Okay, so one of the two happens, but not both. So otherwise, I have an elementary cocycle that contains that first arc that I painted black, and then that elementary cocycle only contains green and black arcs, with all black arcs in that cocycle having the same direction. Okay. I probably will have the TAs do an exercise on this, or we'll do a computer exercise, or you'll have an exercise in an assignment about this, okay? But this is something we will see again. This is a very common activity when dealing with graphs, coloring things. Okay, there's a bunch of coloring properties. Okay, but as I said, I just, for the moment, this is just like for your interest. Maybe think about this. This is some of those properties in graph theory. They're like mind-boggling. The proof of this is not simple. Okay. Now, the fact that I said earlier that we could write those things as vectors sort of should hint at the fact that there is some algebra here. And we're going to see this by thinking about, and I mean, we're not going to go into this into great detail, but we are going to think about it a bit. So these are vectors. What have we seen about vectors? Independence, making bases, etc. Well, I can do the same here. So if I have a bunch of cycles from mu1 to mu k, then I'm going to say exactly the same way as we did for vectors in general, that those cycles are independent. We don't say linearly independent here, but like you see what this means. These cycles are independent if the only way to get a linear combination of those cycles, and really think of them as those vectors, Okay? The only way to get a linear combination of the cycles to be 0 is for the coefficients to all be 0. And then a cycle basis is going to be an independent set of cycles that is going to allow me to write any cycle as a linear combination of the cycles in the basis. And the size of that basis is what is called the cyclomatic number. Okay, it's denoted nu. This is the letter nu. You'll hear me say it a lot, so I'll just write it. The Greek letter nu. So it's denoted nu of G. And this is going to be something that we're going to use. I'm going to show you a little proof a little later. And you'll see that this cyclomatic number is going to be quite important in here. Now, this is not trivial, but let's come back to our example from before. Well, I have 3 cycles there, and maybe let me see if I can erase things in proper time. Yes, looks like it's about okay, so I'm going to, for once, I won't cut out the bad part of when I'm erasing, which in passing is really long. Okay. This thing is really not convenient. Okay, so let me write the vector mu3 here, because I claim that there's a linear combination of mu1, mu2, and mu3 that is the 0 vector. So mu3 is what happens when I follow 2 and then 3. So, and I follow them in the positive direction. So 1, 1, 0, 0, 0. And so when I take mu1 minus mu2 plus mu3, what do I get? I get 1 minus 1 is 0 plus 0. Minus 1 plus 1 is 0. 0 plus 1 minus, 0 minus 1, I'm subtracting mu2. 0 minus 1 plus 1 is 0. 0, 0, and the last one is 0. Okay? So these 3 vectors are not linearly independent. To make a basis of this, I probably could use, so of course, if I take this equation, I can write a mu3 as a function of mu1 and mu2. But if I want to write everything that can happen in terms of cycles, well, I should probably go through 4 and 5, right? If I go through 4 and 5, so I need to be able to describe going through in one direction or the other every single arc here. So how would I do that? Well, if I took mu1, mu2, then I am covering 1, 6, 2, and 3, and probably if I added mu4 to this, I would be able to describe every single cycle, because mu4 goes through 5 and 4, which we hadn't covered in the previous descriptions. And therefore, the cyclomatic number of this graph, nu of G, is equal to 3. Okay? So you can, you remember one of the examples I did earlier about bases involved polynomials. You could also deal with bases that consist of graphs. Cool. Now, this is why the cyclomatic number is important. Suppose I have a graph with n vertices, n arcs, and p connected components. Then the cyclomatic number of that graph is nu of g equals to m minus n plus p. And this is going to be sufficiently important for later use, but I'm actually going to write it here because I will be coming back to this formula quite a few times. And I'll point out this is the number of arcs. This is the order, the number of vertices, and this is the number of connected components. Okay, and that fits right above my head, therefore I don't need to erase it until much later. Let's not worry about where this comes from, but you have this nice relationship in terms of how many cycles you need to describe potential cycles in a graph, okay? Or how many vectors you need in your basis of cycles, in terms of the number of arcs, the order, and the number of connected components. Okay? And we'll make use of that result quite a few times in a proof that I will do in a little while. Okay, so this is it for now. I mean, for proper cycles, but we are going to be exploiting cycles quite heavily. This is taking us to what are called trees and forests. So maybe I'll take a little erasing break for now. I'll be back in a second. Erasing done. Let's come back to trees. So a tree is a connected graph without cycles. And that's a special kind of one graph. Okay? And before I go any further, a forest is a graph whose connected components are trees. So a forest is a graph without cycles. Okay? So let me show you an example. So in graph, I mean, typically when people are drawing trees, although the name suggests a tree, people draw them upside down oftentimes. So I could have something like this. Oops. Things can go in both directions, okay? But they cannot be cycles. So that is a tree, for instance. It's a connected graph, because remember that connectedness does not consider direction. I mean, connectedness in the way we have used it so far. Soon we will talk about strong connectedness, which involves direction. But connectedness in the general sense is just about the existence of an arc, regardless of its orientation. So this is a tree. Okay? There is a chain from any vertex to any other vertex that joins them. So that's a tree, and then a forest would consist of components that are connected. And so a graph with connected components, so like take several of those, and you could think about let me add something else. the graph that consists of these two trees is a forest. Okay, they're connected. There's no cycle. Each one of them is a tree, but the entire graph is not connected. Okay, I have two connected components, this one, and those connected components are trees. Okay, so that's a forest. Now, we're going to spend some time on trees because they are very, very important in a variety of applications. Okay. And we are going to prove this theorem. It's going to take us a little while, probably keep us occupied the remainder of the lecture or almost. So this is a theorem on the characterization of trees. So suppose I have a graph of order n greater than 2. Suppose so more than 2 vertices, then the following properties, they're all equivalent, okay? It's a TFAE, we've seen that already. The following are equivalent. And each one of these, any one of those, each one, being true means that you have a tree, okay? So if I have a graph H with vertex set X and arc set U that satisfies any of those, I have a tree. Okay. So the first property is that H is connected and has no cycles. The second is that H has n-1 arcs and no cycles. The third is that H is connected and has exactly n-1 arcs. Fourth, H has no cycles, and if I add an arc to H, then I create one cycle. Okay? And perhaps, before I go any further, while I'm explaining this, let me erase this because I will use this example tree here to show you what this means. Okay? Where was I? Yes, H has no cycle, and if I add an arc, I create exactly one cycle. So what this is saying here, for instance, is that, okay, so here I have a tree, I add an arc to this tree, I've created a cycle. Okay. H is connected, and if I remove anything, then I lose connectedness. So this again is easy to see here. So I have a connected graph. I was arguing this at the beginning. I have a connected graph, and if I were to cut, let's say, this arc here, then I would have two disjoint graphs. Two connected components, so I would have a forest. By cutting this, I am losing connectedness. Okay. And the last one is that every pair of vertices in H is connected by one and one only chain. I cannot take two different chains of vertices or of arcs to go from one place to another. There is only one way. That's one of the reasons why trees are so important, because they allow you to characterize things in an unambiguous way. Okay, so there is only one way to go from one vertex to another. Okay, so let's prove this. Okay, it's not. I mean, it's important, and at the same time, don't worry too much about it. But let's spend some time showing this. And what we are going to do is we're going to use graph theory, a convenience of graph theory. How would you show a TFAE statement like this? Well, what we are going to do is we're going to make a cycle. So we're going to show that 1 implies 2, which implies 3, which implies 4, which implies 5, which implies 6, which in turn implies 1. So that's why the following are all equivalent. I can pick any property and I can follow this graph onto whatever other property I'm interested in. Okay? So let's start. And I'll point out, as I say, we make abundant use of theorem 34, which is that here, that the cyclomatic number of the graph is m, the number of arcs minus the order plus the number of connected components. So 1 to 2, and I'll keep on coming back to explain what we're doing. So we want to show that 1 implies 2. So H is connected and has no cycle implies that H has n minus arcs and no cycles. So of course, if I assume that H is connected and it has no cycles, then H has no cycles. Okay. So what I want to show is that if H is connected and has no cycle, this means it has n minus 1 arcs. So let's consider the number of connected components, the number of arcs, and the cyclomatic number. Because we're connected, that number here is 1. Okay? Because we have no cycles, I have no basis of cycles to express cycles in, so my cyclomatic number is 0. Okay? So then when I take this, I'm looking for the number of arcs. So I can write that m is nu plus m is mu plus n minus p, which is what we're writing here. Okay, and we find right away that this means that there are n minus 1 arcs. Okay, so we're done. Number 2. Well, 2 implies 3. So we've done this. Let me take them out as we go. Oh, sorry. We've done this, but we still have 2 to 3. So now we want to show that if we have H that has n minus 1 arcs and no cycles, then it is connected and has exactly n minus 1 arcs. And again, like that statement about n minus 1 arcs is in both, so what we need to show is that n minus 1 arcs and no cycles means connected. And again, we're going to use the cyclomatic number and that formula here. Okay? So if I have no cycles, nu of H is 0. And if I'm assuming it has n minus 1 arcs, and then I use the formula, and right away I find that this time I want to see that the graph is connected. That means there's only one connected component. Okay? Well, I compute that P now is nu of H minus m plus n. I substitute those values that I know, and that gives me that P is equal to 1. There's a single connected component. The graph is connected. So this is done. Now I want to show that 3 implies 4. So if I'm connected and I have n minus 1 arcs, then I have no cycles. And if I add an arc, I'm creating 1 cycle, and exactly 1. So let me assume that I'm connected. P equals 1 here, the number of connected components. I have n minus 1 arcs. So m is equal to n minus 1. Then I can easily compute that nu of H is equal to 0. That means there's no cycles. Now let me suppose that I'm adding an arc. So I'm raising m from n minus 1 as it was before to n. Okay, so I suppose that m is equal to n. And I recompute nu of H. Well, nu of H is now equal to 1, which tells me there is 1 cycle in this graph. Okay? So we've done this. Now I need to show that 4 implies 5. So again, I'll go back to the theorem itself. 4 implies 5. I have no cycles, and I add an arc, I create a cycle. And this means that H is connected, and if I remove an arc, then the remaining graph is not connected. Okay? So that's where we are. It's probably the hardest. Suppose I have no cycles. So here I always start with the assumption that, so here this is simply saying what 4 is saying, okay? So assume I have no cycles, so nu of H is equal to 0, and that addition of an arc to H creates exactly 1 cycle. So first, suppose that H is not connected. Then there are 2 vertices in this graph that are not connected. And if I'm adding the arc from one of these vertices to another vertex, then this is not going to create a cycle, okay? Because A and B are not connected. So when I connect them, I'm not creating a cycle. But that contradicts the fact that if I add an arc, I create exactly 1 cycle, which is one of our assumptions, okay, here. So because of this contradiction, it means the graph is connected. And the fact that it's connected, when I plug it in the formula, I get that nu of H is 0, and when I substitute nu of H is 0, p equals 1, I get that m is equal to n minus 1. Okay. Now, let me suppose that now I remove an arc. So what I do when I remove this arc is I get a new graph. And this new graph, it has n prime minus 2. It should not be n prime minus 2, it should be n minus 2. Yes, this should be n minus 2 here, because I start out with n minus 1 arcs, okay? So this n prime should be n minus 2, not n prime minus 2. And this new graph has no cycle. And again, I plug all of this into the formula, and I get that p prime, so the number of connected components in this new graph in which I've removed an arc, is 2. I have 2 connected components. That means my graph is not connected. I can partition my graph into 2 connected components. Okay? 5 implies 6. So we're almost done. 5 implies 6. What do we need to do? We want to show that if I have H connected and I remove an arc, then the graph is not connected. So that's my assumption. And that has to imply that every pair of vertices in H is connected by only one and only one chain. Okay, remember what I was saying. So if I take any 2 vertices here, I can go from here to there, let's say, by only this chain of arcs. So suppose that I have a connected graph, and that if I remove an arc, the remaining graph is not connected. Then if I take any 2 vertices A and B, because the graph is connected, there's a chain between them. Now, that chain has to be unique, because suppose that it is not. Okay. Suppose that, so I have a pair of vertices, my graph is connected, and suppose that I have another chain of vertices, of arcs that I can follow to go from this vertex to this vertex, for example. Well, if I remove, so that means that there are 2 ways to go around to get there. But that means that if I remove one of those ways, so if say there's another way here, say like this, like so. Okay, so I could follow this arc or I could follow that arc. So there are two chains. But if that's the case, when I remove this arc, I'm not disconnecting the graph. Okay? Because I still have my original chain connecting the two vertices. And so that means that removing a vertex, an arc, removing an arc does not make the graph not connected. Therefore, these chains must be unique. Okay? And the final one, so now we're done, and we need to loop the loop. So now we need to show that the sixth property that we just looked at implies the first. So if every pair of vertices is connected by one and only one chain, then that means that H is connected and has no cycle. And that is quite simple. So assume that every pair of vertices is connected by one and only one chain. Now assume that you have a cycle. Then there's at least two vertices that are connected by two distinct chains. And that means that's a contradiction with the fact that each pair of vertices is linked by only one chain. One and only one chain. So we're done. Okay, so, and recall that what that means is now we've shown that if we have any of those properties, if we have any of those, then we have a tree. So this will be useful from time to time. Now, let's move towards what are called spanning trees. And this will be about what we will do for this lecture. But we'll take a little time to get there. So to make our way towards spanning trees, we'll start with the following definition. So we say that a vertex is pendant if it is adjacent to exactly one other vertex. And I remind you that adjacency for vertices means that there is an arc that connects the two. Okay, so we say that a vertex is pendant if it has only one neighbor. Okay, so this vertex is pendant, this vertex is not pendant, because this one is adjacent to three vertices, three other vertices. Okay, but those are pendant. Just in passing, you'll see that in network theory, when we go more towards applications in social networks and so on, some of the ways we are going to look at things, we might call these leaves, because also they're only connected at the tree by one stem. Okay? But here we'll call them pendants. Now there's this theorem that we're going to prove quickly. If I have a tree of order greater than 2, then there's at least two pendant vertices. Okay? The way we prove this is by traveling along the tree. Okay. So suppose we start with a tree of order n greater than 2, so more than two vertices, because of course if we have only two vertices, they're pendant. They're both pendant. Okay, so we want to have another one. And we need a tree. So it needs to be connected. So this is to give you an intuition of what's happening. Okay, so if my order is 2, then every vertex, I mean the two vertices here, are going to be pendant. As soon as I make a tree, so I need the connectedness and I need the absence of cycles, as soon as I make a tree and I add a vertex here, it is not going to work. Okay, I'm not going to be able to produce, and here I'm looking at has at least two pendant, yes, so that one and that one. Okay. Okay, so the way we do is suppose that I have a tree of order n greater than or equal to 2. So I have at least 3 vertices, and I have only 0 or 1 pendant vertex. So suppose I'm a traveler walking along the graph in a cycle way, so I'm not following the path, not following the arrows, I'm just walking along. Whenever there's an edge accessible to an edge or an arc accessible to me, I can go either way, it doesn't matter. Okay? So suppose I'm a traveler on that graph and that I start from a pendant vertex. So I'm starting here, for example. So I have a tree, okay? So I'm taking a pendant vertex. Then what I'm going to do is I'm going to traverse the edges or the arcs, starting here. And if I don't allow myself to use the same edge twice, then I cannot go to the same vertex twice. Okay? There's no cycles, so if I don't say, well, I'll be able to go back and forth here along this one, then I'm never going to encounter the same vertex twice. Okay? Suppose I get to a vertex that I'll call x. Then I can depart x using a new edge. Okay? And x is not a pendant because there are 0 or 1 pendant. Okay? And we've assumed that we started the only place where we had a pendant vertex. So here, let's say, assuming that there are no other pendant vertices, I've started at the only pendant vertex. And so that means that I'm going to be able to go along another path. So that means I can carry on and on and on. But I can't, because the tree is finite. Okay? By assumption. We're not working with infinite trees. So I can't be traveling forever. And that means it's not possible for me to have only 0 or 1 pendant vertices. Okay? And this is sort of used indirectly in the following. So suppose that I have a graph, then it is equivalent for that graph to have a partial graph that is a tree and for G to be connected. So this is going to take a little while to sort of process, mindful of the time, but we're doing good. So a graph, so what's this equivalent? So first of all, remember that a partial graph is the graph that I generate by considering a subset of the arcs. Okay, a subgraph is the graph that I generate by considering a subset of the vertices. A partial graph is the graph that I consider by considering a subset of arcs. Okay. So what that says is that it is equivalent to say that I have a partial graph that is a tree and that G is connected. So what that means in practice is that if I have cycles, okay, let me make this a cycle, then if I omit, this is a connected graph and it has a cycle, but if I get rid of this is, sorry, it's a partial graph, okay? So the graph that I get when I get rid of this arrow in particular is a partial, well, of any arrow, but this is a partial graph. Well, that partial graph is a tree, okay? So being able to find a partial graph that is a tree, it is equivalent to saying that the graph is itself connected. So if I have a connected graph, I can make a tree from that graph. This is essentially the way that it's typically used, but you can think about things both ways. Okay, let's prove this. So let's start with, and I'll just point out what we're doing. This is what I've written here. We want to show equivalence, okay? This is an if and only if. It means I have to show that if I have a graph that has a partial graph that is a tree, then I have connectedness, and vice versa. I want to show that if G is connected, then it has a partial graph that is a tree. So let me start with the contrapposite. So I want to show that G is connected implies that the partial graph implies that G is connected. To do this, I use a contrapposite. So remember, we want to show that P is equivalent to, it's written, so there's no need for me to write it. We want to show that P is equivalent to Q. Well, what we're doing is we're starting with not Q implies not P. This is not, okay? Not Q implies not P, because we know that this is equivalent. The two statements are the same. Not Q implies not P is equivalent to P implies Q. So that first part is used to prove that if a graph has a partial graph that is a tree, then the graph is connected. But we're doing this the wrong way round, not the wrong way round, but we're doing it the other way around. We're showing that if this is wrong, then this is wrong, okay? So suppose G is not connected. Then this means that if my graph is not connected, so look at this graph, for example, it happens to be a tree, but never mind. So look at this graph. If it's not connected, if I remove arcs from it, it's definitely not going to be more connected, or I mean, it's definitely going to lose in connectedness even more. So, and because we're assuming it's not connected to start with, if I start removing arcs from something that is not connected, I'm not making it more connected, okay? So, because G is not connected, no partial graph of G is connected. So, there cannot be a tree, okay? So, the fact that G is not connected implies that there's no partial graph of G that is a tree. And now I take the contrapposite of this. This means that G is connected implies that there's a partial graph of G that is connected. Okay? Cool. Now, let's do the proper wrong direction. Well, back direction. So let's do now G connected implies that there's a partial graph that is a tree. So suppose G is connected. Now, what I'm going to do is I'm going to look for an arc whose removal does not disconnect G. So this means that I'm in a situation, perhaps, where I have something like this. So let me look for an arc in this graph whose removal does not disconnect. If there's none, we're in the situation we were at before where this thing does not exist. Let me hide it away here. So if we can't find an arc which makes the graph disconnected, we're good. We have a tree. We know it by the theorem we saw before. If you remember, here, number 5 says if H is connected and if any arc is removed, the remaining graph is not connected. Well, that's not going to work. Therefore, I have a tree. Okay? But if there is one, such as the one that I've added here, then I remove it. And I look for another one that I can remove while still not disconnecting the tree, the graph. Okay? While I can do that, okay, that's good. When I cannot find another thing to remove without disconnecting the graph, without making it into two connected components, or etc., then what I have is a tree, and the vertex set of that tree is my original graph. Okay? And just in passing, it doesn't, this actually highlights the fact that the spanning tree, because what I get when I do that is I get what is called the spanning tree of the graph. And that spanning tree is not unique normally, okay? Because I was playing with that one and I said, let's remove that one. But nothing says that I should not remove that one. That is a tree again, okay? It's not the same tree we had before, but it's a tree. Okay, it's a spanning tree of the graph. So I can, depending on how I choose to remove arcs, I am not going to get the same spanning tree. And this takes us to spanning tree. Okay. So that thing that I just did when I was removing the arcs that did not cause disconnection of the graph, that allows me to create what's called a spanning tree. But I could also do the following. Take any arc and find an arc that doesn't form a cycle with this guy. And then find another arc that doesn't make a cycle, and etc. And once you've found all these arcs, what you have is a spanning tree. Okay? And this is something you'll do some exercises on. Okay, so don't worry, we'll come back to spanning trees, or at least you will. And that's it for now.